This is part 3 in a series of videos in which I'm attempting to repair and restore this PDP-8M computer. In the first couple of videos I stripped down the chassis, and as you can see I've given the chassis a really good clean. This was surprisingly dirty. It took 4 or 5 passes to get it to this state. It is now quite clean. I've been repairing some of the metal work. There was some damage to the grill. I've still got a bit of work to do on this. I've replaced the bush that had been torn out. Bit of work in various places. You can see it's had a bit of a rough life, and just need to straighten some of the metal work out, but it's not too bad. There's no deep scratches and it's in reasonable condition. I've also been cleaning some of the components like the fans. I don't know if they work yet, but of course I'll test those once I get to basically rebuilding the chassis. But the next thing to do is to get the power supply on the bench. We'll have a look at it, strip it down, clean it, and then give it a full test. Okay, so this is the power supply, and like the rest of the machine, it is absolutely filthy. So the first thing I'm going to do is take it out to the workshop and give it an initial clean. So the way I do this initially is I take it out, actually take it outside, and use a compressor to blow all the loose dirt out. If you do work on one of these and you use that method, I do not advise doing it indoors. After the dust coming off here, it could be anything. So as I say, I'll take it outside, I'll blow all this out, and then we'll strip it down and see what we find underneath the board. Okay, so that's got the loose dirt off it. It doesn't look too bad now, but it is still very dirty. So the next thing is to get this board out. It's just a few screws holding that in place, so we'll get those removed and then we should be able to lift the board out. Okay, so that's the 6 screws taken out that hold the board to the chassis. And what we should be able to do now is rock this board down. And I want this connector to come out. I don't know how long the cables are going to this. They do seem to vary quite a lot. So I just want to pop this connector out to make sure that it's not going to get fouled and we don't want to damage the cables inside. Okay, so now we can feed this through and hopefully lift the board through. Okay, so that's what's on the underside. It's just really all the smoothing capacitors and a lot more dirt. What we can do now is pop these connectors off, and then that will separate the board entirely from the chassis, and we can then have a good look at it and give it a proper clean. Okay, that's the power supply removed from the power supply chassis, and you can see very nice construction. Bit of a pain if you want to just replace one of the power devices, but I can't see any obvious signs of burning. You can see how filthy these get. It's just because the fan blows straight into this, so any dirt lying near the machine gets blown straight into it. So the next thing is this will be given a very thorough clean. The only thing that's concerned me a little bit is the board is fairly badly distorted. It doesn't appear to be cracked anywhere, but it is very distorted. Okay, so I'll get this cleaned, and we can then start testing it and see if it actually works. Okay, I've given the supply a really good clean. Was absolutely filthy, and I can't find any obvious mechanical damage to it, so it's looking quite promising so far. I suspect there is a fault because a couple of the supply leads had been disconnected, so most likely someone was chasing a fault with this. I've given the enclosure a really good clean, so this is now ready when we come to reassemble it. Has got some damage. This section here is bent, so I'll straighten that out. I've taken the residue of the foam that was fitted to this out. It was completely gone. It was just the adhesive backing that was left. You do need to refit this foam. It looks like this, so it's fairly thick, flexible, sticky backed foam. You just cut it to size and put it in. It does need to be in. The reason it's there is because if you have the fan fitted to the end of the power supply, it's blowing air through the supply, and without the foam fitted, if you imagine that this is fitted in this location, and you want as much of the cooling air as you can to go across these cooling fins. If the foam isn't fitted in the bottom of this enclosure, then a lot of the air just goes straight past these large capacitors underneath. Doesn't really do anything. So with the foam fitted, it kind of fills in this underside space. So make sure you do refit that. You might get away with it if you're only using a few cards, but the cards do tend to draw a lot of power, and it does very rapidly increase the temperature of this heatsink and hence the power devices if there's not enough air going through it. Okay, so the supplies themselves are quite straightforward, and if you saw my series on the MDS power supply repair, you'll notice these are very similar types of supply and similar sort of protection. We've got a voltage feedback regulator, overcurrent control and sensor, and then we've got crowbar protection on the output. This can quite often cause problems. Depending on the voltage that you're feeding into the system and how you've got the regulator adjusted and what cards you have fitted, if the voltage goes slightly too high on the output, it effectively short circuits the input, so this thyristor will turn on and it short circuits the incoming DC to ground, and quite often it can blow the fuses or do some damage further downstream. So it's very careful, very important when you adjust this to be careful you don't exceed the trip voltage for the protection, and it's on all of the three supplies. Also, one of the things with this, if you are repairing one of these units, it's very tempting to use a bench supply. I may do that, but you do need to be fairly cautious. If you look at the supply circuit, you'll see this section down here, and this is a staged switch on, so this causes the supplies to generate signals based on the rate at which they come up. So it's kind of a dual step protection, and what this is for is to protect the core memory. What it does is it prevents, and it works when you power off as well, so it's to prevent inadvertent writes to the core memory if the power fails, or when the power is coming up, or when the power is coming down. So this is something you do need to take into account if you are running from a bench supply. It's probably best, if you don't really know exactly how to handle the core memory, it's best to use the supply that came with the unit, because that will make sure that you don't do any harm to it. Talking of the core memory, this is one of the reasons I find these units so interesting, is because they use magnetic core memory. And for anyone that's never really seen core memory in action, it is quite fascinating technology, and because of this, one thing I intend to do in some future videos is to develop a very simple core memory system. So we'll take some magnetic cores, assemble them into a simple memory core mat, and then we'll develop some electronics to allow us to save and retrieve data from them. But for now we'll focus on this, and as we go through, just bear in mind that some of the features of this supply are present because the system supports core memory. Otherwise you wouldn't need some of these features. I'll just grab the schematic again. What we'll do first is check these two fuses. We've got one up here and one down here. We'll make sure they're intact. I suspect there's an issue with this supply because some of the connectors were disconnected. So we'll just check these two fuses first. We've got one here for the minus supply, and that's fine. And we've got another one up here for the plus supply, and that one is actually open. Momentary continuity we've got is because there's a capacitor across here, so you can see as it charges up, this goes on circuit. So this fuse is open, and what we'll have to do is try and figure out why. So that's for the plus supply rail, so that's the raw rail, that's this fuse. Should give us plus 39 volts and feed the plus 5 volt rail, and it should also feed the plus 15 volt rail, which is up here. So with this fuse open, we won't be getting either of these two rails, and of course the system will remain shut down because the power detection circuit will keep it held in the inactive mode. So what we'll do is try and figure out what's going on with this. I'll start by measuring these two devices. We've got this one here, this pass transistor, and this one here, and see if either of those is short circuit. And I'll also measure from this point to ground. It's possible we've got a shorted capacitor here somewhere. Of course, it might be that one of the cards in the system is responsible for killing the supply, but we'll check this first and see how far we get. Okay, so we'll try measuring from this point to ground, and there's nothing showing there, so I don't think we've got any dead shorts across the capacitors. So what we'll do now is we'll check the power devices themselves. Okay, I've got the supply the other way up, so we'll test these. So Q1 is this device at the end, and Q6 is the second one along. So we'll test those two in order. Okay, the first one looks fine, so we'll test the second one. Okay, and that one definitely seems to have issues. So we've got a collector emitter short. So I'll try taking this device out and we'll test it out of circuit and see if we still get a problem. Okay, I've removed the transistor from the supply. We'll give this a quick test. That does actually seem to be working fine, so it's not that that's at fault. So the next candidate is Q7, so we'll test that. I've already been through and disconnected the screw that holds it in place, so we can just flip this over and give it a test. So it's this transistor here. Okay, and that's showing as dead short, so it looks like it might be this transistor. One other thing I've noticed, there's a lot of corrosion underneath this foam, so what I'll do is take this foam off completely. I'll remove this other capacitor and I'll clean all this corrosion off and just make sure there's no breaks in the track. I'll replace the foam and then I can refit the capacitors once we've sorted out the problem with the transistors. But I'll get a lot done off camera, and then I'll get back and see if we've made any progress. So as you can see, with this foam removed, there's quite a lot of corrosion underneath. It traps moisture and causes this issue, and can cause conductive paths to form, so it does need to be dealt with. It used to be there because the capacitors sit directly against this board, so I will have to refit some foam, but I'll clean all this muck off here first and see if we've got any damage to the tracks. Okay, so I've cleaned the corrosion off from underneath the capacitors, and before I refit those I will put some more foam back on the board. It's just double-sided foam to protect the capacitor and the board. And I've also popped out the transistor, so it's this device, so sitting here, and looking at the schematic, that's Q7, and we'll just test that now it's out of circuit and see if it's still reading as faulty. So I've got the meter set to diode test mode, and if we test across this connection, you can see it's reading as dead short. If I reverse this and we test it the other way around, it's still reading as dead short. Now obviously with old devices it can be hard to find data sheets, so what you can do is quite often there's another similar device on the same board. So we've got another one here with exactly the same part number, and we've got a short showing on here between these two pins. So if we test from the same points on this one, we can see it's testing as a regular diode or a transistor junction, and if we test it the other way around, you can see it's looking like a sensible value for a transistor, thus across another transistor. So although it won't give you the exact values and correct readings because it's in the circuit, one thing's for certain, that is if the resistance is very much lower, then that's a fault. It's not going to go higher once it's in the circuit. So this is almost certainly faulty, and what I'll do now is try and figure out what this is and find an equivalent, and see if I can dig one out of the stash, get it fitted, and we'll see if we can get this supply resurrected. Luckily the main power device seems to be intact, so with any luck it is just this. Now because of where this device sits in the schematic, we can see that if it goes short, then it will turn Q6 fully on. Now that would normally cause a very high voltage to be fed into the boards, the 5-volt rail, which would be a bad thing. But I'm hoping what's happened here is that the crowbar protection has done its thing. That shorted out this supply in effect once it got too high. That in turn is what blew the fuse. So I'm hoping the boards aren't damaged, but we'll look at this first and see if we can get the 5-volt rail back to what it should be. Okay, so I've replaced that transistor. That's the one that had failed. Now I didn't have one of these. It's a D45H8 if you're interested, and the nearest I could find that I had lying around was a tip 32. So that's what I fitted. It should work fine. These are not critical. It's just to give like a Darlington driver for the main power transistor to cut down the base current required. And I've checked for shorts on the other capacitors, but what I don't want to do at the moment is just to apply the full power. There is obviously quite a beefy transformer on this, some very big capacitors which I haven't yet refitted. I still have these lying on the bench. So what I'm going to do is test it kind of offline. I'm going to use the bench supply and test these regulators separately. So at the moment I have my Rigel DP-832 hooked up to this point. It's kind of the downstream point of the fuse, and I've got ground of course connected to ground, so I've got them coming in here. So I've got the DP-832 positive coming in here, got it set to 12 volts at 2 amps at the moment, got ground connected to ground, and on the other end I have the meter set or connected to ground, and the 5-volt output, so that's connected to this point. I've got a dummy load connected across the 5-volt rail as well, just to give it something to do. And we're going to be testing this circuit. Now, this is the component that I replaced. This is Q7, and all being well, when I power this up, we should see something around 5 volts. It might need adjusting if someone's been tinkering with this, but it should obviously not go too high. If it does go too high, then chances are the crowbar will kick in. But because we're on the bench supply and it's current limited, then it shouldn't do any harm to anything. So I'll get it powered up. We'll see what the multimeter reads. And as we can see, we're getting 4.7 volts. It's drawing just on an amp, which it should do because we've got a dummy load attached. And we'll see if we can adjust it. So it should be this central adjuster, and it should allow me to set exactly 5 volts. As I said earlier, you need to be careful when adjusting these supplies. If you go too high, then you'll trip the crowbar protection, and most likely you will blow the fuse. So take it very slow. It's very sensitive, single turn pulse, and it's very sensitive. Okay, I'm going to leave it at just under 5 volts for now. It's only drawing around an amp, and what we'll do is when we get it onto the electronic loads is I'll adjust all 3 rails at full power, and then we'll be able to give the supply a proper run. So nothing's getting warm yet. I've got the thermal camera on this as usual, so keeping an eye on this. And what I'm going to do now is increase the input voltage to 20 volts. And we can see a very slight rise in the 5 volt output, but the current being drawn is still the same, so it is definitely regulating. And what I'm going to do now is reassemble the entire power supply and give it a full test and see if it behaves itself. Assuming that I don't get any sparks and smoke when I try and power it up, we'll connect it to some electronic loads and give it a full power test on all 3 rails. One thing with these units is, although it's deemed to be a 115 volt unit, it is actually a split wound primary on the main transformer. Now, this is not my machine, so I'm going to put it back the way it was when I got it, but if you want to, you can rewire these to work directly on 240 volts. Just put the 2 primaries in series. In fact, there was a version of the input card, which is this, that was for 240 volts, and did exactly that. It just put the 2 windings in series. As they are here, there's just a single winding being used. So if you do want to make a permanent change to 240 volts, it is very easy to do that. Okay, so I'll get this reassembled and we'll go from there. Just a quick look before I reassemble this unit. I've refitted the capacitors. Probably can't see it, but I've put some new foam underneath the capacitors, stop them moving around. And I've also refitted some foam into the bottom of the power supply chassis. So I can now reassemble all this, and we'll give it a power up and see what happens. So that's the supply reassembled. I've got it hooked up to the input block. I've bypassed the key switch, but I do have the thermal cutout in circuit. As I said, I've left it as a 115 volt wired unit, and I've got it hooked up to the variac. So we can now power it up. We'll test all 3 rails. We should have a plus 15 rail, a plus 5 and a minus 15. And although we only had a single failure as far as I know, I haven't tested the other rails yet, then all the rails would have been inactive because the way the power supply is designed, the rails have to be all running for the machine to operate. It's to protect the memory contents. Okay, so we'll get this powered up. I've got the meter hooked up to the 5 volt rail, we'll power this up, and as I start to increase the input voltage, the fan should start up and we should see a voltage appearing on the meter. Let's make sure you can see the meter properly. Okay, so already up to 5 volts. Fans starting up on the supply. And we're up to 120 volt input. Okay, but we are getting very high current once we get above a certain point. I suspect that one of the supply rails is going into shutdown, so we'll test those before we go any higher. Sudden spike in the supply current, so we're at 5 volts, that's fine. So minus 14, we'll adjust that. I believe is this adjuster. Keep my hand out of the way. Okay, that's fine. Plus 15, which it is. So we'll keep going up. So the current's still fine at that point, so we'll just check the rails again. And they're all fine. Okay, well, they seem fine. I'm going to do a proper test on the supply. This might just be because of the power factor of the supply, with it having such large capacitors. This variactor's behaving a bit oddly sometimes if the power factor it's feeding is a long way out. So I'll put this on the proper mains analyzer and we'll test the power factor. But certainly all 3 rails seem to be sitting exactly where they should be. Just checking through the thermal camera and it looks fine. Okay, I'll shut this down. Now I had intended to do a full power test on in this video, but unfortunately I don't have a suitable replacement fuse for the one that was blown. It's just a bit of 1 amp fuse wire soldered across at the moment, so I can't go any higher than a few hundred milliamps or it will blow because it feeds both positive rails. So I'll call that quits for this particular video. In the next one we'll look at doing a full power test. I'll get a suitable replacement fuse ordered, get that replaced, and then we can do a full power test on all 3 rails and make sure this supply is working properly. But it seems fine at the moment. All 3 rails seem to regulate nicely, but really until we get some real power on them it's hard to say, but certainly it wasn't working the way it was, and so far it's only cost us a bit of foam and a single transistor.